Hello, my name is Bob D. Hilster, and I am your particle model guru. Today's video is the second video on E equals mc squared. In particular, we're talking about calculating the energy caused by the fission of U-235. Now, if you're new to the particle model, I suggest you watch these two videos. The particle model overview and the levels of the universe. This will give you a much better idea of the whole idea of the particle model and will help you understand some of the individual videos. Okay, we're going to review another video called Energy Mass Equivalence. This is the link to that one, and it does show how to calculate the energy generated by the fusion or fission of U-235 using E equals mc squared. The video starts by explaining about the carbon-12 standard. The carbon-12 has 6 protons and 6 neutrons, and it's exactly 12, and they define it this way. This is the standard for the atomic mass unit. It has exactly 12, and it emphasizes that by showing all these zeros, meaning this is the standard. Carbon-13 has a atomic number of 13, but it has 7 neutrons instead of 6. So the video then says, let's take these apart and see what the mass unit of all the parts are. And he claims that we know what the AMU of each of these are. For the electron, proton, and neutron, and these are the numbers. You can read them just as well as I can, and they take 6 electrons, get that much, 6 protons, you get that much, 6 neutrons, you add them all 3 up, and you don't get 12. You get 12.116001 units. And the video claims that the sum is always more. The sum of the parts is always more than the composite, than the carbon-12 or the U-235 or whatever atom you're talking about. When I hear a statement like this, that it's always more, it seems to me there's a problem. There's a systematic error somewhere. When all the atoms have the error in the same direction, either the theory is wrong or the measurement's wrong or both. Something's wrong here. You might normally expect the variations to be up on some, down on some, if they're close and things are right. But no, these are all in the same direction. And this systematic error, then you go ahead and justify the error by using E equals mc squared. And this error actually has a name. It's called mass defect. And from this video, you get that a mass defect is the difference between the mass of a composite particle, like carbon-12, and the sum of the masses of its parts, like the electron, proton, and neutron. That's defined as the mass defect, and this mass defect can be explained by Albert Einstein's formula E equals mc squared. It makes me wonder why they call it a mass defect. It kind of gives the wrong image. Here's another definition because it brings in the idea of binding energy. The mass defect is the binding energy. The mass defect is true for all nuclei. Here they're talking about only nuclei, but you can also say it about the atom nuclei, that the mass of the nucleus is a little less than the mass of the individual neutrons, protons, and electrons. This is the mass defect. This missing mass is known as the mass defect and represents the binding energy of the nucleus. So this difference they're claiming it's a binding energy. And the video goes on to explain about the nuclear power plant. They use this as an example of energy generated in a nuclear reactor. Fission is used to generate electricity. And it does this by having a nuclear reactor here on this side with U-235 and control rods. And you get the nuclear reaction go, and the energy heats the water, and it's compressed and made steam, and the steam turns the turbines, the turbine turns the generator, and we have electricity. And then you got to cool the water and put cooler water back. So the statement is made over and over again that it's the energy heats the water, and it's a binding energy. Okay, so he then talks about how you split U-235, and there's 3 U-235 atoms, and then 1 nucleon is shot at or comes to this one and breaks it up and breaks it into 5 pieces: a krypton atom, a barium atom, and 3 neutrons. That's the splitting of 1 U-235. Okay, so now we're going to look at the mass just like we did for carbon-12, but this time we're looking at the mass before the reaction and then after the reaction, and he adds up the pieces that are there. Before the reaction, you have U-235 and a neutron, and that adds up to 236.001, and he's using these numbers. These are the numbers we know are true for these elements. After the reaction, you have barium, krypton, and 3 neutrons. You add them together, you get this number, and we have another kind of difference. This difference is where the sum of these parts is less than the 2 that started. It's not the same thing as the carbon-12. Carbon-12, the parts were more than the composite atom. In this case, the parts that result after the splitting are less than what you started with. And you're left with a missing mass of 0.189 atomic mass units. Okay, this is a part, this little strip here equation is from the previous video, if you watched it. And I claim that what you see in this equation is a conservation of particles. And what you saw in the previous slide was that fact that all the particles from where you started before the interaction to after, there was the same number, 236 here, combined to 236. Made boron and krypton, and I put this in red because when you have boron and krypton left over, you don't have all the particles. So they have to add this 3 in order to make it equal. Now, it isn't the 3 that's being just to have conservation markers. So there, I think that's an estimate as to how many neutrons are really being freed up. But if you have conservation of particles, which I agree with, this must be the case. But you also have conservation of mass, except there's a missing mass. This 0.189 mass is missing, and what the video tells you is you can use this mass to calculate the binding energy. So you're going to use E equals mc squared to calculate the energy using the mass. Well, the mass is in units, atomic mass units, not kilograms, and he shows a ratio of 1 atomic mass unit equaling 1.6605 times 10 to the minus 27 kilograms. It's the same as 1 unit. I turn this fraction upside down, multiply it out, you get 3.14 times 10 to the minus 28 kilograms. So now you have mass, you have the speed of light squared, and the energy released by this mass is 2.83 times 10 to the 11th joules. It's pretty small, but when you have a nuclear reaction, you got lots of chain reactions going on, and they're claiming it can add up. So they calculate the mass using this ratio and the energy using equals mc squared, and this is the energy that is released to heat the water. Binding energy is released. I don't know what other energy they might be talking about, but this again is the neutron hitting the U-235, temporarily to 236, splits into barium and krypton and 3 neutrons, and in the process releases the binding energy. And they claim that the energy heats the water. That's never explained. No, I looked all over in the internet. No one explains how energy, as a general concept of energy, even binding energy specifically, how it heats water. No explanation. But they get the energy using the calculation equals mc squared. Okay, well, in the particle model, I've talked about this before, the nuclear binding force. The particle model explains the binding force of the nucleus and the atom using G2 gravity. That's our explanation. The G2 binding force is not part of the nucleus or atom. The G2 particles come from all the stars of the universe. It's coming externally towards all these particles that are grouped together, and they're going to hold the nucleus together, they're going to hold the atom together, and if there's nothing in this space where these particles are passing, then nothing is happening. But if there's an atom there, it's holding it together. It's external. So when the particle model has to explain fusion, you cannot release binding energy because it's not there. There is no binding energy in the nucleus or the atom. So this is the particle model's explanation. It's all about conservation of particles first and momentum second. Particles balance. The number of particles here equals the number of particles here. There is no binding energy stored in the atom, therefore there can be no energy released, and therefore it's not heating the water. What heats the water? The moving objects heat the water. The objects are moving. This is where momentum comes in. What is the velocity of this neutron? Presumably this has no relative velocity. After it splits, these are all moving. They're not moving at speed c. Of course, that's not the explanation of why you have c squared in the equation, but these are clearly not moving at speed c because these cannot go even close to the speed of light. But the momentum here is conserved, and the momentum here, that's what's conserved. You have moving particles, and there is no binding energy released. There is only moving particles, and we know that moving objects can heat water. And this has been my explanation of heat all along. So I claim that the particle model says it's these moving parts that heat the water. And so as a conclusion, E equals mc squared does not explain how fission heats water, and there is no binding energy released. And there is no mass defect. I would claim that there is no, and this is the problem. As far as I'm concerned, there is either the theory is wrong or the measurements are wrong or both to have this mass defect either in the carbon-12, the difference there, or in a nuclear fission. Even though they're in the opposite direction, you have this difference, and it's always the same way. The conclusion for the particle model is that it's the moving atoms and particles that heat the water, not the binding energy. My next video on E equals mc squared will be about measuring the electron's mass, and it's not in kilograms. I'm going to review this video. The video that I'm reviewing is calculating an electron's mass. It's an old one, done very well. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.